In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
In space, threats can come from any direction. Meteors from deep space, invisible but deadly bursts of radiation from the sun, otherworldly landslides from above, and Marsquakes from below.
Outer space is the last place you want to be as a human being.
What makes fire more deadly in orbit than on Earth? What happens to someone exposed to the harsh extremes of outer space?
The saliva, the blood, goes from a liquid state to a gaseous state.
Buckle up and prepare for space disasters. The year is 2030. A crew of astronauts simply hits the up button in a space elevator. The elevator will bring them to their spacecraft, which will meet them in orbit. They're grateful they don't have to risk the controlled explosion of a rocket launch.
We can now create carbon nanotube fibers that are stronger than steel. And believe it or not, they are strong enough to keep a space elevator afloat in space so that you can literally climb your way into the heavens.
The 60,000-mile cable is attached to the docking station that revolves at the same rate as the Earth. Just like a geosynchronous satellite, it stays over a fixed spot on the ground. A space elevator would be any astronaut's dream. But the space elevator dream can also turn into a nightmare.
The space elevator has to be anchored to the Earth. But what happens if you have storms and all of a sudden the moorings begin to snap?
With the cable still attached up in space, it will start swinging wildly, striking objects hundreds of miles away in any direction. It's also possible that some type of guidance computer or thruster problem could knock the platform in space off course, snapping the cable at the top. If it happened while a crew is going up or down the cable, they would be in for the last ride of their lives. And the 60,000 miles of cable hurtling toward Earth is long enough to wrap itself around the planet almost 3 times at the equator, creating havoc over a wide area.
It would be not only disastrous and dangerous for the people involved, the kinetic energy of something like that whipping through the atmosphere would be a menace to navigation. So it's going to have an inherent danger in it that any human system has.
This is just one of many potential disasters facing future space explorers. Living in space will also involve grave dangers. Colonies on the Moon or Mars will be faced with threats from all directions, especially above, where sudden spikes of radiation can turn deadly.
If we were walking around on the surface of the Moon, I would say our #1 concern should be solar flare. The sun erupts. The protons coming from that flare could kill an astronaut. There have been several flares over the last couple decades, which if we had had astronauts on the Moon just walking around in a spacesuit would have been lethal for them.
On Earth, we're protected from most radiation. Earth's atmosphere and magnetic field are like a protective fence, letting only a fraction of particles through. On the Moon and Mars, you are directly in the firing line. The Moon has no atmosphere or magnetic field. Mars has very little atmosphere and only weak localized magnetic fields. NASA takes the solar flare threat seriously because it has already come close to killing Apollo astronauts.
The Apollo lunar landing crews were quite fortunate. In 1972, in August, there was a major solar flare. There was what they call the Great Solar Storm that happened to just take place in between the Apollo 16 mission in April and the Apollo 17 mission in December of that year. Had that occurred while there was a crew on the surface of the Moon, they would have been dead.
The effects would be similar to certain people who died in Hiroshima and Nagasaki, those who were not killed in the initial blast, but were overwhelmed by the extreme radiation dosage within several seconds. An astronaut caught in that situation will have little time to react. A flood of deadly particles penetrates the body, killing all of the astronaut's cells in a few brief moments. So it's no surprise that space colonists will need to be constantly on alert.
We're going to need weather reports, but they're going to be space weather reports. We're going to need satellites monitoring the sun, giving us advance warning of flares. The light from the sun takes only 8 minutes to reach the Moon. Coming behind it would be the particles, the lethal radiation. You'd have minutes, half an hour, that sort of time frame before you wanted to really be in a shelter. Such a storm might last for a couple days.
One option for protection is living underground. But don't let the barren terrain fool you. The Moon and Mars are still active bodies where natural disasters like those seen on Earth can strike.
I'm here in the Mojave Desert in a cave created by a lava flow, underneath 5 or 6 feet of rocks. Well, being underground in a cave may be an option for habitation on the Moon or on Mars. On the surface of the Moon and Mars, there's radiation from the sun, there's cosmic radiation. On Mars, there's dust storms. If we're underground, well, we're safe from those hazards, but we have other hazards. Imagine being in this cave when there's quakes, rocks falling down, crushing us, pinning us.
A Moon or Mars quake could also threaten an above-ground colony. The Moon and Mars don't have tectonic plates like the ones that cause most of Earth's quakes and volcanic eruptions, and there are no signs of active volcanoes. But the Moon and Mars do have hot cores. So as the pressure from that heat heads to the surface, the shaking starts. And where there's quakes, there's often another disaster.
Just recently, we've seen a landslide occurring on Mars. It was captured with the cameras in orbit. So we know this does happen. And that can be hard to predict. We might put our base someplace which appears perfectly safe, and then a few years later realize that there's a landslide hazard.
Scientists are still unsure what started the 2008 landslide near the North Pole of Mars. It was in an icy area, and researchers believe most of the slide material was ice. That's just the type of place a colony might be located to take advantage of converting the ice to drinkable water. Even a distant quake could still trigger a slide near a colony. But what if a hidden fault line is running right under the buildings? In the future, space colonists living on the Moon or Mars will have plenty of threats to deal with, including natural disasters like moonquakes and Marsquakes.
They're not active the way we're used to on Earth. They're active in different ways, and there may be unexpected ways that they could cause problems for us.
Since our current knowledge of these other worlds has literally only scratched the surface, it's possible that in the future we could locate a base right over a fault line without realizing what's below. And since weight is always an issue when carrying things into space, the lightweight buildings could be quite vulnerable, especially the outer layer.
If anything happens to that protective layer, that's trouble, very rapid trouble, as the gases stream out of the habitat. You've got to have a very efficient and quick procedure for getting into a spacesuit to survive that sort of decompression.
Death would not be instantaneous if oxygen and atmospheric pressure inside the colony are suddenly lost. On Mars, there is a thin atmosphere, although it's not breathable, since it's mostly carbon dioxide. On the Moon, there is only the vacuum of space. But you'd still have a chance, as we've learned from industrial accidents in vacuum chambers on Earth.
Exposure for maybe a minute or so is survivable. Now, if you stay in a vacuum long enough, there's not enough oxygen, so nitrogen that's saturated in your blood and your tissues comes out of solution and causes bubbles. That's decompression sickness. And also, if you hold your breath, you can get what they call pulmonary overinflation, and your lung ruptures into your bloodstream, and that's called an embolism. So there's multiple factors that can result in death from exposure to the vacuum of space.
Then there's the temperature extremes. Temperatures on the Moon go from a high of about 240 degrees Fahrenheit down to around 290 below. Mars can get just as cold. Although you could get lucky and have a nice 70-degree summer day. But without a breathable atmosphere, going outside without a spacesuit is still a very bad idea. Another thing above-ground space colonists will have to be on the lookout for is meteors. The craters on the Moon tell the story. It's an easy target.
We're relatively comfortable down here underneath these layers of protection. We've got a thick atmosphere which absorbs and burns up meteorites. We go to the Moon, nothing. There's no thick atmosphere. We are exposed to everything that space is throwing at us. We go to Mars, there's a thin atmosphere, but it's not anywhere near as good as the Earth's. Again, we're exposed to what's coming in from space.
Smaller meteors that are only inches or fractions of an inch wide, known as micrometeoroids, will strike most often and without warning.
You're walking along the surface of Mars, and something the size of a grain of sand comes slamming into your spacesuit. That's going to be a serious problem. It's going to be a loss of the pressure in the spacesuit. It could mean loss of life of an astronaut. When we have lots of people doing a lot of work on other worlds, eventually that's going to happen. That's the equivalent of a lightning strike, a rare, possibly fatal event.
Micrometeoroids could also punch a hole through the wall of a colony building. Like space stations, colonies will probably be built in a series of sections or modules. And just as crews have had to seal off sections of a space station in an emergency, colonists will likely do the same. Large meteors will hopefully be tracked, so the colonists will know they're coming. But evacuation might not do any good. A nearby strike would still send out a deadly shockwave for miles. A 10-foot wide meteor hits with the explosive equivalent of 6,000 to 8,000 tons of TNT. Flying debris could also damage colony buildings beyond repair. And anything approaching a direct hit, there'll be little evidence that the colonists were ever there. It's unlikely that colonists would live anywhere near one of Mars's volcanoes. And the moon probably hasn't seen volcanic activity in the last few billion years. But even ancient remnants of volcanoes could still cause trouble for crews in vehicles.
Both the moon and Mars show evidence of volcanic flows. So we might expect to find there this sort of thing, volcanic caves. Now imagine driving along the surface, come across one of these, you're not expecting it. That could ruin your day, it could ruin your vehicle. You could be at the bottom of this pit without any way to get up. Even worse would be imagining one of these volcanic caves with a thin layer of volcanic rock on top of it. You move across on top of that, it gives, and down you go.
But not all colony disasters will be so dramatic. Simply running out of supplies is one of the greatest dangers. Since the moon is much closer, emergency supplies could arrive in a matter of days. With Mars, help is many months to years away, depending on how the planets are aligned.
On Mars, if something goes wrong and you lose some supplies, resupply from Earth can be 2 or 3 years away. You think you've got enough to last, you lose half of it through an accident, you're dead. It's a real problem. I think that means you're going to have more than what you need. You're going to have enough for 5, 6 years.
Living in space much closer to home, on space stations and longer shuttle flights, has already taught us a lot about the dangers of space. And fire is space crew enemy #1.
The reason fire is such a threat is because spacecraft traditionally have higher levels of oxygen than the atmosphere, certainly in higher concentrations under pressure. They're also filled with electronic equipment. Electronic equipment puts out heat, and often there are sparks and arcs. It's a bad combination.
Luckily, designers have made it easier for crews to put out fires where all of those miles of wire lurk behind the control panels.
This is a mock-up of the Space Shuttle flight deck that we use for training of crews. If you look at the various panels we have, you will see small holes like this at various locations around it. And these are for fire extinguishers, so that if there is a fire behind one of these panels, you can put an extinguisher in there to extinguish the fire.
Andrew Thomas knows a thing or two about fires in space. While on the Mir space station in 1998, a fire suddenly broke out.
All the smoke was pumped right out into the cabin.
Crews hurtle through space in their enclosed craft, desperate to maintain the Earth-like atmosphere inside. Out here, fire is one of the biggest threats. In 1998, NASA astronaut Andrew Thomas is on board the Mir space station with 2 Russian cosmonauts. Suddenly, a fire breaks out. Ironically, the fire starts while cleaning what's known as an air scrubber, one of the filters designed to remove exhaled carbon dioxide and other toxins from the space crew's environment.
All the smoke was pumped right out into the cabin, and so all of a sudden the cabin in one part of the space station just became thick with a pall of smoke. And of course, all the air handlers then moved all that smoke around the spacecraft. So within about 2 hours, the entire spacecraft was completely filled with smoke. So we had to just wait for the air handlers to scrub all of this contamination out. And that took about 2 days. And we all manifested symptoms of the toxicity of that environment. When there's a lot of carbon monoxide at those levels, you have nausea, a certain amount of confusion, invariably a headache because you're oxygen deprived. It's just a very uncomfortable feeling.
The dangers of fire in space go beyond the fact that you can't open a window or call the fire department. Fire actually behaves differently inside a spacecraft in zero gravity.
What we are seeing is a candle flame. The bottom one is a candle in normal gravity. And as you can see, the flame moves up because buoyancy pushes the hot gases around the flame up. The top photograph is the same candle, but in the absence of gravity.
Columbia Spacecraft Park for the module. A mist burn will be initiated here in about 15 seconds.
The hot gases don't move up, and what you have is an spherical flame.
There's the flame. So here's the initial light off for combustion module 2.
So putting a smoke detector on the ceiling, like we do on Earth, doesn't work in space. Instead, detectors are located next to small suction devices that draw air and any smoke or other toxins toward the detector. To figure out just how dangerous fire is in space, Professor Fernandez-Peyo's team performs experiments in the University of California, Berkeley Combustion Lab and on KC-135 aircraft in short bursts of zero-G. In theory, fires in zero gravity should be less intense because the hot gases don't rise, which means cool air isn't drawn in at the base to keep feeding the flames. But they're finding that the reality inside a spacecraft is more dangerous. Air conditioning systems create small air currents. Those currents bring fresh air, or in this case, fuel, to the fire. At the same time, the low airflow and lack of gravity don't remove the heat as quickly as on Earth. The result?
This type of fires are hotter and more dangerous than in normal gravity.
And fire is likely to become even more of a safety hazard inside the new Ares Orion spacecraft being designed to replace the shuttle.
What they've decided to do was to reduce the pressure and increase the oxygen. And by doing this, they reduce the preparation time that it takes for the astronauts to go from the vehicle to outside of the vehicle. So what we're doing is we're testing materials at that proposed environment. We've learned that for the environment that they've chosen for the next generation of vehicles, things actually ignite about 20% faster than they would in the current environment.
The combination of high oxygen content and low airflow means just about anything can catch fire, even metal. In a worst-case future scenario, a space station crew is unable to quickly extinguish a fire. It grows too fast to seal off in a separate module. Even if they put on emergency oxygen masks, the heat of the flames will likely kill them. And if they're somehow able to survive the flames, the filtering system is completely overloaded. They are left to die in a toxic stew from smoke inhalation. The best chance of survival with an out-of-control fire is to abandon ship and return in a re-entry capsule if one is available. That was the key to the survival of the crew of Apollo 13. April 11th, 1970, the three-man crew launches into space. 2 days later, on their way to the moon, an oxygen tank suddenly explodes. The explosion causes a substantial loss of oxygen and damages the service module's electrical system. The crew is forced to live in the cramped lunar capsule.
Apollo 13 is the classic case of the failure that doesn't kill you. It happened at the right time. It happened when they were on their way to the moon, so they could use the lunar module as a lifeboat and get back to Earth. Had the same problem occurred after the lunar landing, when Lovell, Swigert, and Hayes were on their way back to Earth, there would have been nothing they could do. They would have been dead.
The threat of fire is especially high inside spacesuits. During spacewalks, also known as EVAs or extravehicular activity, the spacesuits need to be kept at low pressures. Working at a fraction of Earth's atmosphere is the key to flexibility.
If you had a spacesuit that was at 1 atmosphere, you would be like basically in a balloon, and you couldn't move.
With low pressure, just like a climber in the thin atmosphere of Mount Everest, astronauts need to breathe highly flammable 100% oxygen.
This is an arm from the spacesuit. It was burned up in a fire in 1980 at Johnson Space Center. Just doing some checkout tests, pressurizing the system with the 2 different oxygen sources. And when this fire occurred, it was, quite a shock. People were standing nearby it, and someone was supposed to be in the suit the next day for a manned test, and it could have been a fatal fire. Even as it is, this suit is worth, at the time, $3.1 million. And it also took NASA $20 million to recover from this fire in terms of redesigning the suit.
Extravehicular activity is dangerous for many other reasons as well. In fact, the world's first spacewalk almost ended in disaster.
Alexei Leonov did the first spacewalk that any human did in 1965. But in the rush to accomplish that space spectacular and thereby beat the Americans, the Soviets took some shortcuts on the safety of the cosmonaut. And so he blew up like the Michelin Man.
The suit became rigid. It couldn't handle the pressure differences between the breathable atmosphere inside and the vacuum of space.
The problem is you've got a spacecraft in the Soyuz capsule that he was flying that's very small, and the hatch for it is even smaller. Ultimately, his response was to let a little bit of the air out and just deflate the thing enough so that he could crawl back in through the hatch. But he will tell you that to this day, that he wasn't sure he'd be able to make it.
An astronaut having, like Leonov, to let the pressure out in order to be able to maneuver in it is in the same situation as a diver ascending from deep water too quickly. Nitrogen bubbles will form in your bloodstream and not only be painful, they'll kill you.
And during EVAs, a simple thing such as an unsecured tether or a misfiring emergency thruster can also spell disaster. Being outside of a spacecraft on a spacewalk is the most dangerous thing an astronaut in orbit can do. One false move can be deadly, especially if that false move takes you away from the spacecraft.
There was an instance on one of the Russian space stations, the Soyuz, where one of the crew members was not tethered, and he was in the airlock area watching the other crew member, and he slowly started to drift out, and the other cosmonaut saw him and grabbed him. An untethered person in space without appropriate propulsion system to get back would be very, very serious. I mean, basically, you're lost at sea.
Even with a propulsion system, it can fail or run out of its limited propellant supply before the astronaut reaches safety. The astronaut will simply keep floating off into space. The International Space Station is unable to chase someone down, and if the shuttle were docked, it would take too long to undock and mount a rescue. In this nightmare scenario, the astronaut will likely have several hours of oxygen remaining to contemplate the end. As long as the suit is intact, pressure will not be an issue. Either the oxygen will run out, or the system, which removes exhaled carbon dioxide, will stop working. Either way, the astronaut will suffocate and continue floating into the emptiness of space. The same micrometeoroids that can devastate space colonies also pose a lethal threat to spacewalks and entire spacecraft. Plus, in low Earth orbit, these rocky little gremlins have company, space junk. And all of these things are racing around at over 22,000 miles an hour. At these speeds, objects that are only a fraction of an inch wide can be deadly.
A micrometeoroid flying through space is a lot like a golf ball flying through the air, with these differences. The micrometeoroid is much, much smaller. And because it travels at hypervelocity, it's far more destructive when it hits. If a micrometeoroid hits your spacesuit, it's going to put a hole in it. You don't have reach or the ability to patch or fix it, unless you've got a fellow astronaut right there. You're going to die. Your air is going to leak out fairly quickly. It's going to gush out. Your blood's going to boil. That's going to be it.
And what causes blood to boil? Well, in space, boiling blood has nothing to do with heat. It's all about the sudden lack of atmospheric pressure.
The idea that blood boils is really a misnomer. The liquid in your body goes from a liquid state to a gaseous state.
There have been many tales about what happens to an unprotected person in outer space. Here's the real story. As the vacuum of space fills the spacewalker's leaking suit, the liquid parts of the tongue and eyes begin to bubble, along with all of the saliva, internal fluids, and blood. As the blood turns to gas, oxygen no longer travels to the brain or anywhere else. The brain shuts down within about 15 seconds, leaving the victim unconscious. Soon after, the rest of the cells in the body die. Temperature extremes could also play a role, since the sunlit areas of space reach 250 degrees Fahrenheit, and the shaded areas quickly plummet to 250 degrees below zero. And just how big a hole is too big for a spacesuit?
You're really asking a very small amount of material to stop a particle that could be coming in at 7 kilometers per second. You can see the entry hole from the test, and it has many, many layers, ending with what's called the bladder. And this is a pressure retaining layer. That's about a 2 to 3 millimeter hole, a 4 millimeter for an EVA suit on the soft goods. This material would be considered catastrophic.
Luckily, no one in space has ever suffered this fate. Impacts can also cause trouble in sneakier ways. So NASA goes to great lengths to simulate different types of micrometeoroid damage down on Earth. Researchers inside the hypervelocity building of the White Sands Test Facility in New Mexico create impacts using compressed hydrogen gas guns. These guns definitely bring the heat, shooting objects up to 19,000 miles per hour at shuttle and space station parts to assess the damage.
At that velocity, you can get from Los Angeles to New York in about 8 minutes. The testing that we're going to perform today is on an International Space Station handle that the astronauts use on the outside of the space station in order to transverse around the space station safely. Several astronauts have cut their gloves severely. This is a great concern to NASA because when they design the space station, they are very careful to eliminate all sharp edges because you don't want something snagging the astronaut spacesuits and creating a hole and ending a mission.
Technicians mount the handle in the target chamber, place the tiny 1/32 of an inch wide projectile within a holder that will disintegrate once fired, then add gunpowder to the breech.
We take gunpowder and propel a piston which compresses hydrogen gas up to about 100,000 psi. It's that highly compressed gas that accelerates the projectiles from 0 to 19,000 miles per hour. We use 3 different types of cameras. One takes a snapshot, another one takes a film, and the third type is a digital camera, which takes 16 frames at 200 million frames per second.
The technicians retreat behind a blast shield and prepare to fire. The chamber is cleared of oxygen and other gases to simulate the vacuum of outer space. Now, the moment of truth. How much damage did this simulated micrometeoroid cause?
Even though it is a small impact, there's enough of a lip with enough structure so that an astronaut could catch their glove on such a lip and cause a tear in their glove.
And if a projectile only 1/32 of an inch wide can cause this type of damage, you won't believe what a larger object can do. At the NASA White Sands Test Facility in New Mexico, researchers load small projectiles into huge guns. The projectiles simulate micrometeoroids and space junk. They slam into spacecraft parts at up to 19,000 miles an hour, creating disasters on Earth to better understand disasters in space. At such incredibly high speeds, a very small object can cause very big trouble.
I'm standing inside of our largest target chamber of our 1-inch gun. The gun is 175 feet long and can launch up to a 3/4 inch size projectile. I'm holding a target that was impacted with a 5/8 inch projectile, and as you can see, this is the entry hole, and it went all the way through the test article. An impact of this size would be a catastrophic event in space.
The only hope the International Space Station crew would have for survival is to put on emergency breathing masks and head to the re-entry capsule. An object less than an inch wide would have forced them to abandon this multi-billion-dollar facility. That type of scenario is the reason why crews are constantly adding extra layers of protection to the outside of the space station. For another type of space collision, we have only ourselves to blame. In 1997, a Russian cosmonaut had trouble guiding an unmanned cargo craft to its docking point with the Mir space station.
Now, we know in aviation that 70% of the accidents are human-related, so it wouldn't surprise you to think that humans have also a big role in accidents and mishaps in space. The Mir collision actually was because a crew member complained that he wasn't trained enough to do the rendezvous, and the ground control team said, well, you have to do it anyway. The hit occurred and it caused a leak in the cabin pressure, so now they started to lose cabin pressure. And then the space station started to tumble because it was like pool balls. One hits another, it causes it to move. So even a minor thing, just the control of a rendezvous and docking could have almost catastrophic consequence.
But the disasters that have happened in space still pale in comparison to the disasters of getting into space and returning. There is a saying that the first 50 miles and the last 50 miles are the most dangerous part of any mission. The 1986 Challenger launch disaster and the 2003 Columbia re-entry tragedy make that clear. But if we're ever going to travel beyond our solar system, we're going to need to move beyond our current rocket technology. One possibility that both thrills and terrifies is known as an antimatter engine. Inside massive particle accelerators, scientists have created minute amounts of antimatter, which is made of atoms that have the opposite charges of normal atoms. So with antimatter, the electrons are positive and the protons are negative. When matter and antimatter come into contact, they annihilate each other, releasing tremendous amounts of energy.
Antimatter engines have a 100% conversion rate of matter into energy. Realize that even an atomic bomb is only 1% efficient. Only 1% of the mass of an atomic bomb is converted to energy. In an antimatter engine, We're talking about nearly 100% of the mass converted into energy. It is, for the next century, the propulsion system of choice. But there's a problem.
A teaspoon of antimatter might be able to propel us across the solar system. But that same teaspoon also has the power to destroy an entire city. And once a spacecraft is out in deep space, simple accidents can suddenly tip the balance from life to death. As we venture to Mars and beyond, with journeys lasting years at a time, the chances of becoming stranded in space will become much greater.
For example, on a flight to Mars, what if a micrometeoroid punches an oxygen tank? What if you just are simply running out of breathable air? There is nothing you can do. You can die graciously is what you can do, however long it takes.
Another source of disasters, especially with journeys measured in years, is something that many people overlook.
One thing we forget is our fellow man, our fellow astronauts. If you're cooped up in this tiny little space capsule for, let's say, a year at a time going to Mars, or years going into deep space, you can go crazy. You can get claustrophobic. The guy next door could really get on your nerves, and you want to strangle him after a certain point.
Although the incidents aren't highly publicized, crew members have had problems getting along in the past with dangerous results.
There was at least one Soviet space station crew of the 1970s that didn't get along pretty famously and actually supposedly had a fist fight. These stresses are going to manifest themselves on these long-duration missions. Anybody who thinks they aren't is fooling himself.
And to make things even more interesting, Russian cosmonauts supposedly have firearms stowed on board as a precaution after an extremely off-course landing in 1965.
The crew landed up in the woods in Siberia and were there for about 3 days. And they had to fight off wolves until they were rescued. After that particular mission, the Soviets decided that they were going to put a sawed-off shotgun in every Soyuz capsule in case something like that happened again.
The cosmonauts are now rumored to have handguns stored in emergency kits. But no one is eager to offer any official details of guns in space. And the risk of having a weapon aboard isn't just a concern if tempers flare.
There is actually a documented case of a payload specialist who flew on a shuttle flight, whose experiment failed, and he spent his whole life getting this experiment ready. It failed, and he actually talked about killing himself. And the crew themselves actually tried to protect him and guarded the hatch so he wouldn't kill them.
Even with all of the space travel lessons learned so far, one thing is clear. Nothing can completely prevent disasters from striking in the future.
If we're going to continue human spaceflight, we have to accept the risk because it is a very dangerous occupation. But we have to manage the risk, and that's going to require good technical people and good leadership.
But just as surely as disasters will strike, there is another certainty when it comes to manned space exploration.
I think we have a gene for exploration, a gene for discovery. Not only is it good for our evolution, because we find new avenues to reproduce and to colonize, but I think it's also inside the spirit of human beings to want to know what's out there. Is it possible to reach areas that we've never been before? And the thrill of being the first person to explore new terrain, that's fantastic.